Hello, we shall now turn to another application of Fourier series, the basic convergence theorem, to prove a certain identity involving Bessel's functions. We shall later use this in the application to celestial mechanics that was promised. So let us begin with the definition of Bessel's functions of the first kind. The Bessel's functions of the first kind of order k is denoted by jkz. I want to point out that this is defined for all k real numbers or even complex numbers, but we are concerned here primarily with k non-negative integer. So we are going to assume that k is an integer and k is non-negative. And the definition of the Bessel's function is given in the slide 1.26. jkz equal to summation k from 0 to infinity minus 1 to the power n divided by n factorial into n plus k factorial z upon 2 raised to the power k plus 2n. It's a power series. It's an ordinary power series. What is the radius of convergence of this power series? How does one find the radius of convergence of any power series? The first thing that comes to mind is to apply the ratio test. One can actually apply the ratio test here, and one checks immediately that the radius of convergence is infinite. So when the power series has infinite radius of convergence, then the sum of the power series is a holomorphic function on the entire complex plane. Holomorphic is the same as analytic. In classical literature and in books such as Churchill Brown, you see the word analytic functions, they are the same. So holomorphic function or analytic function defined on the whole complex plane. Such a function is called an entire function. So when a power series has infinite radius of convergence, the sum is an entire function. Other examples of entire function: e to the power z, sine z, cos z, they are all entire functions. A polynomial is an entire function. And one more example of an entire function are these functions jkz, the Bessel's functions of the first kind of order k. Here are some exercises. Show that the series converges for all z. I already indicated you must use ratio test. A power series can be differentiated term by term inside the disk of convergence. Here the disk of convergence is a whole of C. So you can differentiate the power series as many times as you want. And the derivative jk prime z is obtained by simply differentiating the series term by term. You simply differentiate all the terms and carry the differentiation under the summation sign. Now the second exercise says prove that z to the power k jk prime is z to the power k jk minus 1 z. The second exercise is z to the power minus k jk z prime equal to z to the power minus k jk plus 1 z. And the third exercise follows immediately from the second exercise. So you try these exercises, they are very easy. You simply have to multiply 1.26 by z to the power k, and then you have to differentiate term by term. So I shall assume that you will do these exercises and we have these identities. We are going to use the third exercise. The first part of the third exercise will be used. All right. Now let's see. So the Bessel's functions are defined for all k, not just for integers, and you can easily check that the Bessel's functions satisfies this second order ordinary differential equation z squared y double prime plus zy prime plus z squared minus k squared y equal to 0. And when k is a negative integer, we shall make a convention that jkz equals minus 1 to the power k into j sub minus kz. Equation 1.28 that you see on the slide. So now we've got the sequence jkz for all k ranging from minus infinity to plus infinity. Whenever you've got a sequence, it is of interest to construct the corresponding generating function. The generating function for the sequence jkz is by definition the formal series gzt equal to summation k from minus infinity to infinity t to the power k jkz, equation 1.29 that you see on the slide. That's a generating function. Of course, it's not very clear that the series converges. It is not difficult to show that the series converges. The fact that the series converges for all t not equal to 0 is left as an exercise. An elementary estimate. Now let us obtain a basic estimate for the absolute value of mod jkz. We'll use this to prove the Schloemilch's formula presently. So let's begin with the definition of the Bessel's function. Jkz equal to summation n from 0 to infinity minus 1 to the power n upon n factorial into n plus k factorial z upon 2 to the power k plus 2n. Let's take the absolute value and let's use triangle inequality and take the absolute value inside. Mod jkz less than or equal to summation n from 0 to infinity 1 upon n factorial into n plus k factorial into mod z by 2 the whole thing to the power k plus 2n. Now let us multiply and divide by 2n plus k factorial. What do you get? Mod jkz less than or equal to summation n from 0 to infinity 2n plus k factorial upon n factorial into n plus k factorial into 1 upon 2n plus k factorial into mod z by 2 the whole thing to the power k plus 2n. Now let us observe the emergence of a certain binomial coefficient. So what is appearing? The binomial coefficient is appearing 2n plus k choose n. What is 2n plus k choose n? It will be 2n plus k factorial upon n factorial into n plus k factorial, and that is less than or equal to 2 to the power 2n plus k. Remember that n choose k is less than or equal to 2 to the power n. That's an elementary inequality. So using this inequality, we get mod jkz less than or equal to summation n from 0 to infinity mod z to the power k plus 2n upon 2n plus k factorial. What's going on is that you see the 2n plus k factorial upon n factorial into n plus k factorial cancels the 1 upon 2 to the power k plus 2n. If you look at the last displayed formula in the slide, you see that there's a binomial coefficient 2n plus k choose n, and there's a 1 upon 2 to the power k plus 2n. These two things cancel out each other. And so we have the inequality mod jkz is less than or equal to summation n from 0 to infinity mod z to the power k plus 2n divided by 2n plus k factorial. Take out the mod z to the power k outside the summation and divide and multiply by k factorial. So we get mod jkz less than or equal to z to the power k mod upon k factorial into summation k factorial into 2n plus k factorial into mod z to the power 2n. Now let us look at the ratio of the two factorials under the summation sign. 1 upon 2n plus k factorial. 1 upon 2n plus k factorial is 1 upon 2n factorial into 1 upon 2n plus 1, 1 upon 2n plus 2, 1 upon 2n plus k. So k factorial upon 2n plus k factorial will be what? 1 upon 2n factorial into 1 upon 2n plus 1, 2 upon 2n plus 2, etc. k upon 2n plus k. Now these last k of them are all less than 1. 1 upon 2n plus 1 is less than 1. 2 upon 2n plus 2 is less than 1, etc. So we are just left with a 1 upon 2n factorial. So we get finally mod jkz less than or equal to mod z to the power k upon k factorial into summation n from 0 to infinity mod z to the power 2n upon 2n factorial. So we get the useful estimate mod jkz less than or equal to mod z to the power k upon k factorial into hyperbolic cos mod z. Use the estimate that we have just obtained to prove that the series 1.29 for gkzt converges. What is this 1.29? You see it on the slide. Gzk is summation k from minus infinity to infinity t to the power k jkz. This series will converge for all values of z and for all non-zero values of t. It's exactly to establish the convergence of this series that we need the elementary estimate that we just established, mod jkz less than or equal to mod z to the power k upon k factorial cos hyperbolic mod z. Let us now proceed further. We shall derive the following formula of Schloemilch. The Schloemilch's formula is displayed on the slide. It's equation number 1.30. The series k from minus infinity to infinity t to the power k jkz converges, and the sum is exponential of zt by 2 minus z upon 2t. Let us proceed to the proof of this theorem. Let us denote the sum on the left hand side by gzt. Let us differentiate term by term. With respect to z, how can I differentiate a series with respect to z? Look at the exercise on the slide. The series converges and the convergence is uniform on compact subsets. When you have a series of holomorphic functions, when you have a series of analytic functions converging uniformly on compact sets, term by term differentiation is valid. So this series sigma t to the power k jkz can be differentiated term by term with respect to z. What happens when you differentiate it? It is summation k from minus infinity to infinity t to the power k jk prime z. Now what is jk prime z? Let's go back and look at the third exercise on the displayed slide. The first part of the third exercise. 2 times jk prime equal to jk minus 1 minus jk plus 1. Here in this slide, wherever there is jk prime z, you replace it by 1/2 of jk minus 1 minus jk plus 1. That's exactly what I have done. Now, split this sum into 2. So, del g by del z is t by 2 k from minus infinity to infinity t to the power k minus 1 jk minus 1. And the other can be written as minus 1 upon 2t summation k from minus infinity to infinity t to the power k plus 1 jk plus 1. Each of the two individual series is again gzt. So gzt is a common factor and we got t by 2 minus 1 upon 2t. So we get the differential equation del g by del z equal to t by 2 minus 1 upon 2t g of z comma t. From this we immediately get the formula for gzt. Gzt is g of 0t into exponential of tz by 2 minus z upon 2t. What is g of 0t? Go back to the definition of g. G is given by g of z comma t is summation k from minus infinity to infinity t to the power k jkz. Let us put z equal to 0 in this equation. let us put z equal to 0, we simply get t to the power k jk of 0 summation with respect to k. So we must understand what is jk of 0. To understand what is jk of 0, let us go back to the definition of jk. In equation 1.26, you put z equal to 0. What do you get? You get 0 provided k is 1, 2, 3, etc. If k is 0, 1.26 has a constant term, and that constant term is 1. So J0 of 0 is 1 and JK0 is 0 when k is 1, 2, 3, etc. So we get G of 0 comma t is straight away 1 and we get the formula GZT equal to exponential of TZ by 2 minus Z upon 2t. And the proof of Schloemilch's formula is complete. Now let us derive a simple consequence of the Schloemilch's formula. Here it is very tempting to put t equal to e to the power I theta. Suppose I put t equal to e to the power I theta, what happens to the quantity under the exponential? Z is a common factor. We got 1/2 of e to the power I theta minus e to the power minus I theta, which is exactly sine theta. So that gives us a very interesting consequence we shall now examine. We are going to derive an integral representation for these Bessel's functions jkz. So what is the integral representation for the Bessel's function jkz? That you see as theorem 13. Jkz equals 1 upon pi integral 0 to pi cosine of z sine theta minus k theta d theta for integer values of k and k non-negative. Equation 1.31. So as I indicated, let us put t equal to e to the power I theta in Schloemilch's formula and we get summation k from minus infinity to infinity jkz e to the power I k theta is exponential of z into 1/2 of e to the power I theta minus e to the power minus I theta, that is exponential of iz sine theta. You get exponential of iz sine theta. Now you observe that 1.32 is a Fourier series. The left hand side of 1.32 is a Fourier series. Only difference is that I have written the series in complex form. Remember, our Fourier series was a0 plus a1 cos x plus b1 sin x, etc. But if you write cos x as 1/2 of e to the power ix plus e to the power minus ix, sin x as 1 upon 2i into e to the power ix minus e to the power minus ix, and rearrange the whole thing, we get a Fourier series described in terms of exponentials, complex exponentials. So the left hand side of 1.32 is actually a Fourier series. How do you find the Fourier coefficients? Multiply 1.32 by e to the power minus ik theta and integrate over minus pi pi. On the left hand side, only one term will survive. It will be jk, and you are going to get at the left hand side 2 pi times jk. I had divided by the 2 pi, and so I get jk equal to 1 upon 2 pi integral minus pi to pi exponential of iz sine theta minus ik theta. Now we must write the exponential in terms of cosine and sine. Exponential of iz sine theta minus ik theta, what is that going to be? It is going to be cos of z sine theta minus k theta plus I times sine of z sine theta minus k theta. Now let us look at this sine of z sine theta minus k theta. What do you know about this function? Is it an odd function or is it an even function? Let's pause and let's think about this. Sine of z sine theta minus k theta is an odd function. So when you integrate an odd function from minus pi to pi, you get 0. So only the cosine term will survive in the integral. What I just said is now on the slide. You see the exponential being written as cosine and I sine terms. The term involving sine will drop out since it's an odd function and we're integrating from minus pi to pi, and the integral over cosine will survive, and that is exactly the formula 1.31 that was displayed in theorem 13, and that completes the integral representation for jkz. In fact, this is the form in which Bessel originally introduced the functions that bear his name. This formula is going to be extremely important because we are going to use this in connection with the problem on celestial mechanics that was promised earlier. So we have obtained an integral representation for jkz. What is the use of this integral representation? Of course, as I promised, we are going to give an application to a problem in celestial mechanics, but that apart, the integral representation can also be used for a variety of other purposes. Here I list 3 of them. First, to show that jkz is infinitely many zeros on the real axis. The second use is to obtain decay properties of the Bessel's function along the real axis. The Bessel's function decay to 0 as x goes to infinity. To prove that, you use these integral representations. We use this integral representation to obtain asymptotic behavior of jkx for x large and real. So these are 3 uses for the integral representation that we have just derived. Here are some exercises. The first exercise has already been indicated earlier. It has just been repeated here. Show that jkz satisfies the differential equation z squared y double prime plus zy prime plus z squared minus k squared y equal to 0. The second exercise is show that x j0x is a solution of y double prime plus y equal to minus j1x. The third part is an addition formula for the Bessel's function. You may remember that e to the power x plus y is e to the power x into e to the power y. Sine of x plus y is sin x cos y plus cos x sin y. Cos of x plus y is cos x cos y minus sin x sin y. Similarly, Jn of x plus y can be expressed in terms of jkx and jly. What is it? Jn of x plus y is summation from minus infinity to infinity jkx into jn minus ky. The formula is slightly more complicated than the formula for sine or cosine. So this completes the first chapter on the basic convergence theorem.